And you guys should be able to see my screen now. You see it? Perfect. Never mind. No one said anything. I see something. That's what I said perfect about. But can you guys see it?
Yep.
Okay, cool. Come on, show up. Okay. So the cool thing about your substitution and elimination reactions, they pretty much do the same thing. Like for substitution, SN1 and SN2, they both like substitute a leaving group and replace it with a nucleophile, whatever nucleophile you have. The only thing is there's small minor differences, but they still do the same thing at the very end. The big thing for SN2 is the inversion of stereochemistry or backside attack. I'm probably going to talk more about this later during tomorrow's review session. That might be tomorrow afternoon. I still have to pick a time because my flight is at like 9. For backside attacks, I usually think like an inversion of an umbrella. Hold on, I forgot my other notes. One sec. Here we go. And even though they do the same thing, they attack different things. That's another big difference between SN2 and SN1. All right. So this one, we have an inversion. This one, we don't have an inversion. We actually get both. There's a carbocation intermediate, hence it can attack either R or S. So your product can be both R and S isomers. If there is a stereocenter, it attacks. Additionally, it only attacks, or SN2 only attacks methyl groups. I usually do it as 0' methyl, primary, and secondary. It's really easy, especially if your nucleophile is a weak base. A thing to note is that a weak base, I'm just going to denote it as B, any weak base. And hopefully you guys are able to recognize what they are, because a weak base is something that's not NaNH2, not NaOH, obviously, not NaOCH3, not the strong bases we have. So anything else, when in doubt, you can just assume it's a weak base. I know that might sound bad, but it's a lot easier to memorize your strong bases and then catch up with the weak bases later on, because there's a lot more weak bases you'll see. And the weak bases, they can only do SN2. They cannot eliminate anything because they're that weak. They're nucleophiles, but they would rather just attack the nucleus of a carbon atom. A strong base is very nucleophilic and can just rip off a proton, which is just a nucleus, and just rip it off an entire complex. So a weak base will just want to substitute something. So as a general trend, weak base is always SN2. A strong base, sometimes, it kind of depends if it's primary or not, or if it's allylic or benzoic, but we'll have to look at that later. Now that we know what does SN2, how I usually tackle these reactions, all right, well, look at these two groups right here. Which one is going to be the leaving group? Cl or Br?
BR.
Br. It's the most stable the most stable anion out of the leaving groups. And obviously we know the periodic trends with conjugate base and pKa, but another way I look at it is Br is a lot bigger. And this is probably going to be an aqueous solution. So those water molecules will be able to, or this one is, the solvent is DMSO, but if it was aqueous, it's a good leaving group because those water molecules better stabilize a large surface area relatively for bromine. That's me looking at it as like a Gen Chem perspective. I'm also a Gen Chem TA. But for looking at this, we know that Br is a leaving group. And when we do the backside attack, all I do is that I keep everything the way it is, and I just move what's on the wedge to the dashed. Like this Br out of here. This Cl will go right here. Just stick it onto where that dashed was, Cl, and then whatever base you have right here, you can stick on that new wedged. And let's say it's like, I don't know, a nitrile group. So our nucleophile, whatever it is, attacks this side and basically inverts this umbrella this way. And that's all I do. Like whatever groups I have here that's not wedged or dashed, I just keep them the same. Because in all honesty, I just the wedged and the dashed, I throw out the dashed, put the wedged where that dashed was, and I put the new thing on the wedged. There's only 2 spots that I really fuck with. So that's kind of it. And then SN1, there's no stereochemistry because you get a racemic mixture. There is stereochemistry, but it's not exclusive. And this is tertiary only because there's a carbocation intermediate. And again, tertiary carbons are kind of the ideal for carbocations because it's hyperconjugated by neighboring carbons. Obviously, it can also be conjugated by double bonds that could resonate with it. But that's, those are the exceptions that we're looking at. But for the most part, tertiary only, secondary and primary if it's benzylic or allylic. But for the most part, it's going to be tertiary. And again, it's racemic. R plus S. So for here, what's our leaving group? It's going to be Br like we did before. So if Br is leaving and we're putting this, our nucleophile is CH3O. And I can put it in any way I want because, again, there's no stereochemistry like necessary. You can do like both products. Personally, I'll accept either one because it's right. If you're right, you're not wrong. And SN2, or not SN2, SN1 reactions, that's when your base is your solvent. That's only when you have one reactant. And obviously you have a temperature that dictates if it's E1 or SN1. But if you only have one thing there, which most of the time it's gonna be H2O, CH3OH. Those are your 2 big ones. And then maybe like 10% of the time you'll do ethanol, CH3, CH2OH. But those are the main things you're gonna be seeing. Yeah. Hopefully you guys know SN1 only corresponds with low temperatures, so that's 0 degrees. Going to elimination, we just basically create a double bond. So elimination, how I look at it, is the reverse of an addition, because in addition, we destroy a double bond and we just basically add, all right, HCl, Cl, and then H. And then the reverse would be the elimination, some kind of strong base would come in and swoop that hydrogen, just take it out. And at the same time, those electrons would go to that bond right there. And then then that carbon chlorine bond would go to the leaving group and it can just up and leave. So this is what we have. I think to note is knowing your alpha and your betas. Like this. The only hydrogens that can be stolen are from beta carbons. It cannot steal it from an alpha carbon, so no hydrogen there can be taken. It has to be from a beta carbon, a beta hydrogen. I don't know why I'm doing that. A very common small strong base is just NaOH. Negative charge. Out of these 2, which one would it take? Well, it has 2 to choose from. Out of these beta carbons, they each have hydrogens. And let's ignore the periplanar stuff because they actually have more hydrogens, obviously. So it doesn't really matter which one they take. Which one would they rather take? Well, if you have a small strong base, it's going to be Zaitsev. So you have a secondary and you have a primary over here. It's going to want to take those secondary hydrogens and just steal it out of there. And with that, electrons from that original hydrogen carbon bond goes there. The electrons in the chlorine go there, and it just leaves. This is the intermediate. I'm just trying to redraw the arrows. That way you have an alkene where you have H2O and then just chlorine. The big thing is the concept of anti-periplanar. Now, this is the easiest form you can look at it. If it gives you cyclohexane or something like that, and you're looking for anti-periplanar, well, you're just looking for something that's on a different plane of BR. Because like if you have a Hayworth structure that looks like this, if you were to convert it into this, let me fill this in. BR, H, let's do HCH3. All right, which hydrogen would a strong base take? Well, it can't take it from an alpha hydrogen, and these are our beta hydrogens. Which one's anti-periplanar? Well, there's only one that's on a different plane. That's what we're looking for. Because again, I'll just do OH. It'll come in and swoop something that's far away or away from your leaving group. So if your BR is wedged, well, we're looking for something that must be dashed. So we can't go here because that's an alpha hydrogen. You only have this one and you have this one. Which one's anti-periplanar? Well, BR is wedged, so we have to go with a dashed. If this dashed one is being taken, then our new product would be this. It looked like that. Obviously, you have an H right here. All right. E2 is the same thing, but again, it's not very regio selective. There's a carbocation intermediate, but the big thing, it's always Zaitsev. Always, because it's a carbocation intermediate. Wherever you go, has to follow the Zaitsev rule, has to be Markovnikov, right? So the same deal as SN1. You have a nucleophile that's also your solvent, except this time it's at high temperatures. At low temperatures is SN1, and at high temperatures is at E1. And hold up, E1. So if we're looking at here, all right, well, this is our alpha carbon. These are beta carbons, beta. Over here, if we were to draw out our hydrogens, which one would it take? Well, it has to be Zaitsev. So it has to be one of these two. And there's only one way it can go. It goes towards the secondary carbon. All right. Now, I'm just going to throw some weird situations here. I think this is on your problem set that I was drawing. Someone asked me to go over, I forgot who, but I thought this was a pretty neat one. So the first, or the way I do it is I just write out everything I know. All right, leading group is secondary. We have a small, strong base, and I look for it in the chart. All right, secondary, small, strong base, that's going to be an E2 Zaitsev product. All right, well, let's look at this. We have a quaternary carbon, we have a secondary carbon. This is just our alpha, so that doesn't do anything. Well, quaternary, something you have to remember, there is no beta hydrogens. It's all connected to carbons. Same thing if it was phenyl. So if you had something like this, Br, pH, all right, well, this pH actually looks like a bond that's phenyl or benzoic. This carbon right here, that's sp2. There are no hydrogens. So that's the thing. Beta carbons have to have beta hydrogens in order to do an E2. And in the situations I just presented, this one has no hydrogens. This one does. So even if Zaitsev, there's only one direction to go, and that would be this way. So if our small strong base was OCH3, and there's something to note, I think I talked about that in the review session part 1 I recorded that I'll post later. Counterions are usually going to be potassium, lithium, or sodium. It's just Na plus, because in an aqueous solution, it'll dissociate, and that's just a notation of writing, all right, this is what we're actually looking at. Just a nucleophile with that negative formal charge, which obviously basic. This will come in, swoop one of those hydrogens, and a double bond will form here, where those electrons go here, then the electrons on that bromine would leave. So you would get the thing is, there's 2 hydrogens it can take. I'm just going to leave a bromine. I don't think you guys have a mechanism question, but if you do, don't forget to leave those every single product possible. We have cis and trans isomers. And thankfully, he actually went over in class on which one is the most abundant. And that's going to be the top one. The top one is the most abundant what we want because it's trans. There's the intermediate has least steric strain, not intermediate. For E1, yeah, but this is just normal E2. There's less steric strain in general for that nucleophile to steal hydrogen. So this is our major product. You're welcome on the problem set or on the test to draw both products and just label or circle one of them. Just any indication that we have. Yeah, I guess that's it. This is a pretty cohesive chart of all of these charts put together. Well, actually, I built these last 2 charts stemming from this, but what he gave you, last year I just drank a bunch of caffeine, sat down to the math MPO. I don't know why. I think I was getting boba, and I hammed this out in an hour, and then I crashed for a good while. But it was pretty cool when I woke up. I'm like, wow, I did this. It is pretty accurate because what basically inspired me to do this is there's so many different rules, mainly around benzylic and allylic, that I had to basically, I needed to insert it in the chart he gave us. But looking at this, don't forget, when nucleophiles equals our solvent, it can only do tertiary. So no matter what, secondary, primary, or methyl, you can just do no reaction. Same thing with weak bases and tertiary, no reaction. And that's already a good bit of what you have. That's around 40% of the chart already, just no reaction. I think this one might be the trickiest spot because small strong base, unless it's methyl, strong bases usually do E2 reactions, but it's only when you have a primary one, it does SN2. I might go over that chart a little bit later, maybe during a recession tomorrow. I'm gonna stop my share. Does anyone have any specific questions? Because right now, from where we're at right now, I'm probably gonna go over the chart of predict the product using SN2, E2, E1, SN1 for the review session mechanisms, and then make our way down to problem set 9 once we get the hang of it. But does anyone have any anything they want to interject or questions that you want me to go over? Can you guys hear me?
Yeah.
Okay, cool. I might just go over, you know what? Screw it. Let's do the problem set first and then the review session slide. Let's do that. Let me download it real quick. I downloaded it on my laptop and on my iPad. Problem set 9. Cool. Alrighty. Let me share my screen again. Come on. All right. You guys should see this. All right. Now, using the approach I talked about, all right, let's let's identify what we're working with. Our leaving group is primary. What we have is a small, strong base. Primary small, strong base, well, that's going to be a SN2. Hold up. I'm going to burp, I think. Never mind, I guess not. Okay. Do you guys see the practice test I posted?
Yep.
Okay, cool. Oh, excuse me. I'm so sorry. Okay. It's going to be SN2. OCH3. That's it. Even though it's SN2, it's a backside attack. There's no stereochemistry here because this carbon that we're taking, or the leaving group is leaving, it's not a stereocenter. There's 2 hydrogens on it, and it's just a substitution. We look down here, we have again, primary, large strong base, and there's E2. And the thing you have to note is when you have only one direction to go for E2, you cannot write Zaitsev or Hoffman. You have to just write E2, because in prior tests, he has made it clear that if you write Zaitsev or Hoffman where it's not needed, he can take off points. I don't know what his stance is for the summer, but stuff like this elimination would just need labeling E2 if you were to come across it in the chart, because there's only one direction to go. There's one direction to go. There's neither Zaitsev nor Hoffman. It's just a simple E2. This one, primary, it's E2. Neither Zaitsev or Hoffman, because there's only one direction to go right there. That's our double bond. Right here, we have a secondary, small, strong base. That's going to be E2, Zaitsev. However, one of the exceptions that he'll throw at you is when you have a leaving group that's a bad leaving group like fluorine, most of the time for this test, it's going to be fluorine. So if you see fluorine, know that you just change this to Hoffman. Because out of these beta hydrogens, for a bad leaving group, we'll take the least substituted one. All right, and right here we have a secondary. But if you look right here, we have a weak base, right? Weak base, they can only do SN2, and it's not tertiary, so it should work. If it was tertiary, there'd be no reaction, obviously. So if it's SN2, well, let's just redraw it out. And dashed. Our leaving group is thankfully already on a dashed position, so that leaves, and we leave our H there. Our prior CH3 over here, we just plop it on that dashed. And then whatever nucleophile we have, SH, we just stick it right there, and boom, you're done. If you write it like this, CH3, H, SH, and as long as you write stereochemistry, this is S, as long as you write that, you'll be fine. But I don't see why you wouldn't just draw it like this. It's a lot easier to just, again, flip that over to the wedged, not wedged, the dashed. Now this stuff is what we're looking at in terms of anti-periplanar. Hopefully you guys are able to apply what we just learned to this. So if our leaving group is dashed, our hydrogen that we take, beta hydrogen, has to be wedged, the opposite. Well, let's look at our hydrogens. We have one, nope, that's too big. 1, 2, 3, 4. We can't take the one on alpha. And out of these 3, which one is anti-periplanar? There's only one. So we have to take that one. So this leaves, electrons go here. So our double bond form right here. H, CH3. Right? Yeah, that's it. Now this one is also a little tricky. Well, our leaving group is bromine. It's wedged again. So let's look at our beta hydrogens. Beta, beta. But this is also beta. You see, this is a tertiary carbon. Tertiary, even though SN2 cannot work on a tertiary, E2 can. Even as tertiary, it'll take, because it's not directly attacking that alpha carbon, it's just taking something beta to it. So E2 can just basically sideswipe any beta hydrogen. Obviously, it's selective because we just learned that, but it can just sideswipe a relatively far away hydrogen and then cause an elimination reaction. Well, we have to look at something anti-periplanar. This hydrogen cannot be taken. This hydrogen cannot be taken. However, this C is not a stereocenter. It has hydrogens in a tetrahedral shape in every direction. So whatever small, strong base we have can take any single one of these hydrogens. And thus a double bond will be formed with that beta carbon. There we go. Nope, wrong one. H3. HCH3. That's our answer. All right. Before we move forward, something I just want to make sure again, a cool checkpoint to take a look at is making sure whatever compound you have is sp3. Because if you notice for these substitution reactions, that's sp3, sp3, sp3. All right. Because if you look at an sp2 carbon right here, this is what he was talking about in class, sp2, like let's do Br, H. Well, if you had a weak base, like let's do, gosh, I don't know. Let me think of a funky one. See, nah, let's just do NaCN. And then, I don't know, THF. NaCN. There's no backside attack because that's sp3, not sp3, sp2. So the moment you see an sp2, it's a pretty good idea to just write no reaction, because for elimination substitution, it's not going to really react with sp2. Same thing with elimination. Let's do something like this. Br. All right. If you had something like a small strong base, all right, something that would large strong base, something that would induce a excuse me, an E2 reaction. Well, that's allylic. It cannot form a double bond there. So it has to be a substitution reaction. That was a bad one. I don't know why I did that. I need something that's just sp2. Oh, like this. This is our alpha carbon. This is our beta carbon. Some small, not small, but any kind of strong base can't really take that hydrogen away and cause it to make a triple bond, because this is sp2. So sp2 carbons aren't really reactive with our substitution and elimination reactions, at least for this set. I think the first test you tackle in semester 2 deals with sp2 reactions, and benzene, but that's for Dr. Berg or whatever OChem teacher you have. So something to note. We might see that in the review session slide. Now right here, we're actually use two products, show both, and then circle the major product. All right, well, let's take a look. Bromine, that is a tertiary bromine or leaving group, and we have a small strong base. So tertiary small strong base, well, that's E2 Zaitsev. So it's E2 Zaitsev. Well, where can double bonds be formed? Well, this has a beta hydrogen. I don't know, not that color. Beta hydrogen right here and beta hydrogen right here. There's 3 of them. So our 2 products would be, let's do H2 phenyl, and then there we go. Those would be our 2 products, because our original alpha carbon was right here. And there can be no double bond being formed with that phenyl, because again, that phenyl group is a benzene ring. Let me just redraw it out. This is what our compound looked like, CH3. This is our phenyl group. That's sp2, and there are no hydrogens on there. So there's no hydrogens that can be taken. There's no double bond that can be formed. So out of these two, which one is going to be the major product? Well, it's small, strong base, so we need to choose the Zaitsev product. And that would be the one on the right, because this is primary, this is tertiary, which is what we want. That's our Zaitsev product. Over here, this is what we just did. Excuse me. There are two products to choose the right one. And that is our stereochemistry. I'm just going to write this out and not redo it because we did it earlier. And again, the one we would want is the one that's trans because that has the least steric strain. Does anyone have any questions regarding this problem set? Anyone have any questions in general? Is everyone following through so far?
Yeah, I'm like following you, but it's like so much information at once. You kind of just have to like sit with it for a second.
Yeah, don't worry. I'll give you guys a little bit before we tackle the one slide. Here, let me share my screen and go back. I'm going to pause the recording, resume recording. Great. This is the stuff from the review session video, so have fun. Yep. All right, let's take a look at these. All right. We have a secondary leaving group. Pretty sure, right? One, two. Yeah, okay, secondary. I'm not going crazy. And weak base. Well, weak base, it's not tertiary. That screams SN2. So it is SN2. CH2. See? Anything that's not dashed or wedge, I just like to keep it as it is. And then I just swap places. So this isn't necessarily on a dash, but it kind of works backwards too. If that was on the dash of our leaving group, whatever is on the opposite one, right? If our leaving group is wedged, our hydrogen's dashed, let's just put that hydrogen right there. All right. And our weak base attacks from, I'd say, from into the page towards us, out of the page, just into that carbon. So our SH will be right there. I don't want to say stuff like that because it gives me flashbacks to physics, the right-hand rule and shit. Not a lot of fun. Anyone here take physics or gonna take physics?
Just finished the two I did in the spring. Yeah.
What's up? Sorry, I didn't see who said that. I heard, who's the second person?
Probably me. I just finished physics 2 in the spring.
Yeah,
same here.
yeah.
Or
Out of
should
the
I
page,
say
into the
I
page, I'm
barely
like
got
right-hand
fruit
rule.
physics?
I'm like,
Should I say I barely got fruit physics 2?
Survived it.
Same. Did you guys have Crichton?
Yeah, he was the only one.
I had con.
Oh, bro.
Really?
Like Crichton. Okay, that's beyond the point. I'm done with physics. Get that shit out of here. Not right now, at least. Okay. Going back down, bromine, our leaving group is again secondary. Weak base. And usually for SN2 reactions, anything that's polar but aprotic is a really good solvent because it stabilizes that concerted reaction, but it doesn't actually, act as a nucleophile. It just, the polarity helps. You'll deal with that in lab. I think when you guys do like the Grignard reaction, it's pretty cool. I say that, but it took us forever because I think they ran out of one ingredient, but that's okay. We're looking at it like this. That's the only carbon we're looking at. So this CH3 doesn't really do anything. And we have a dashed hydrogen there. Well, that dashed hydrogen now becomes wedged. And our newly added nucleophile, CN, takes place at that dash now. Going down here. All right. Our leaving group is primary. However, that's an sp2 carbon. This is a small strong base. Yeah, they can't really substitute. Yeah, because there's no backside attack. There's just no reaction. I don't know what else to talk about with that. It's kind of self-explanatory. There's no sp2 carbons can't really do much with the stuff we're learning. Here, one of the cases where our nucleophile is the same as our solvent and is at low temperatures. So nucleophile equals solvent. We have a secondary carbon. Normally, that would be no reaction because remember, nucleophiles equal solvents can only work on tertiary, leaving groups. However, even though this is secondary, it's also benzylic. If this is an SN1 or E1, there's a carbocation intermediate right there, but that carbocation is stabilized by allylic door hinge maneuvers. You know, all the resonance structures provided by any allylic structure or a benzylic structure. So it's stabilized, so it can work. And if it's at low temperatures, is that SN1 or E1? It's going to be SN1. So OCH2CH3. Racemic mixture of any stereochemistry there. So it doesn't really matter. Right here we have a large strong base. We have a secondary. And this is tertiary. Secondary. Large strong base. Which one do we want to go to? Well, excuse me. Secondary large strong base, that's our Hoffman product. So we have to go to the least substituted one. And look, no, something like this. In contrast, same thing, secondary, small strong base. We have a tertiary, secondary still, but this is a small strong base, so we have to go with the Zaitsev. It looks something like that. All right, let's take it from the top. Small strong base. This bromine, that's tertiary. Tertiary small strong base, that's screaming out E2. Well, let's look for E2 reactions. We have to look for an anti-periplanar hydrogen. There's no hydrogens on the alpha. Even if there were, it wouldn't react. The beta hydrogens right here and right here are on the same plane as the bromine. So no matter what, they can't be anti-periplanar. Because if you remember from test 1, if they're on the same plane, the pattern would be axial, equatorial, axial. No matter which way you flip the chair, they will never be axial to each other. So these ones are out of the picture. But again, we have a carbon right here with 3 very healthy and scrumptious hydrogens that can just be plucked away. So it would form like this. That small strong base would come in and swoop that hydrogen. And yeah, something like this. CH3 still, that's a really terrible wedge. CH3, then H, that'd be our product. Right here, we have a weak base. That's going to be, that can only do SN2. However, SN2, that's an sp2 carbon. Can't really do anything. There's no reaction. This is what we saw in our problem set. We have fluorine, but that's our leaving group. That's going to be a secondary, and we have a small strong base. Normally, small strong base secondary, that screams out E2 Zaitsev. However, bad leaving group, fluorine, the one exception, changes that into a Hoffman product. So it'd look like that. And our last one, all right, leading group is secondary, small strong base, secondary. Well, that screams out E2. And excuse me, H. Now, this is a tricky situation. All right, there's no methyl group here. So there's no applicable beta hydrogens. What can it do? Would it be no reaction? Not necessarily. It would do in SN2 because reactants, they can do SN2, albeit very slowly. They will. So don't forget there's a wedged hydrogen. That hydrogen would now become dashed. And our former wedge would now become a nucleophile. CH3. This is an SN2 reaction. That might seem really weird, which it is really weird, and we can tell because that's extremely slow. It is very, very slow in real life, but it still works. Yeah. All right, that's kind of what I really wanted to cover today. Yeah, I'm gonna stop my share. You guys have any last minute questions? Because whatever I didn't cover in the recorded review session, I'll probably cover tomorrow, and that usually goes, or that's with the more on the E2 with the anti-periplanar stuff. If you guys here, let me just share it one more time so you guys can see what I'm talking about. It's this stuff, like working with Newman projections is really easy once you know what's going on, and then synthesis. So that should make up for everything.
So
Yeah.
you're going to be having a review session tomorrow, is what you're saying? Or you
Probably.
just- Okay, cool.
I'm gonna have to see how much I do or don't have to pack because I've been covering a bunch of shifts because I'll be gone from work for like an entire week. So I'll have to see.
About what time do you think you'll have?
Probably in the
if you do have-
afternoon.
Okay.
You know, honestly, what time do you think would work for you guys the best?
I mean, like, yeah, this time worked fine for me.
Yeah, I'm not gonna do like super late. I'm not gonna do super early. So probably sometime between like 2 or 4. That's when
Okay,
it's gonna
cool.
start. Yeah, and it's a Saturday. I'm not gonna do anything for. I'm not gonna make
Yeah.
you guys come to something in the nighttime or the morning. You're good.
All right, cool. Thanks.
Yeah, of course.